Welcome everybody. Hello, and let's start with our lecture and continue our considerations from yesterday. Yesterday we talked about these problems of least squares estimation of linear dynamic systems in particular. We talked about the question whether the estimation is consistent. Consistent, remember, means bias-free. So the parameters we get are the same, the parameters the system has, if the system is really linear, of course. And second, we do not have an infinite variance, so we can trust our estimation. That's the basic idea. These are sufficient conditions, and interesting enough, we find such a solution, but we get a consistent estimation for dynamic system, but there is a problem. The assumptions of proposition 5.3 have to be fulfilled. Therefore, going back to these assumptions, meaning here we are. First of all, either the bias is zero if E and M are uncorrelated, and you already know that this is usually not the case because we have this filtering of the disturbances via A of Z to the power of -1. So we can put it in that way. If E is generated through such a Joule-Walker equation, then everything is good, but usually that's not the case. So as said, we cannot influence our electrons to move, that they behave like we want to. So obviously there are some problems with that. Of course, epsilon and eta, so in this equation here in the middle, it's specifically epsilon is white noise if this equation here is equal to 1, which is the case if A1 up to AN 0. So, and back to our problem at the initial setting, A1 to AN is 0 if we have just a moving average problem. So for moving average estimations, we can estimate the parameters consistently in any case as far as the output noise is white. And we are happy. So better to say correctly, it's a sufficient condition. If the output noise is white, then we get a correct estimation for the parameters B1, B2, B3, etc. But this is usually not the case that we always have a moving average process, moving average system. Very often we find autoregressive parts, and therefore A1 to AN are not 0. And then we are confronted with this problem. And okay, as engineers, we can say, yes, just look at noise-free processes, also possible. This quite often happens. So if you look in identification books, they will say this is the end of the world because you will not find something because that's the problem. And I say as an engineer, well, I can set up my experimental setting very often and can set up the meters, basically voltage meters, amperemeters, velocities, all that. So very often I have this in my hand. So as an engineer, I can say, yes, I construct the experiment from which we want to gain knowledge about A1, A2, A3 in such a way that this holds, and then I'm also happy. So that's why it's okay to say the system is almost noiseless. But of course, there are also situations where this does not happen, and where we have the problem that we cannot construct this. This is typically the case if we are in an online setting. There we have cheap sensors which have to be applied, because noiseless sensors. If you think of voltage meters and you look at the high-end voltage meter range, you pay 500 euros or so for your lab equipment. Of course, a voltage meter is used in a car hundreds of times just to measure the voltage in any place of every computing unit, just to see whether we have over voltage or lower voltages. And now, of course, it's clear that we can't use always 500 euros for this voltage meter. And these voltage meters are much cheaper, not that precise, not noiseless, etc. So in this setting, very often we are confronted with the situation that we have noise and we have to deal with that. And that's the story of today. We want to talk about how to find solutions to that problem. Is it possible to get an estimate of A and B parameters, even if there is noise? And the wonderful answer is there is a solution, and it's generated around the word. Comes slide. Oh, sorry. Here we are. This is the motivation about instrumental variables. That's the starting point. So this is a specific method which is today the gold standard if you want to identify the parameters of linearly problems, linear dynamic systems. And therefore, it's implemented, for example, in MATLAB, but elsewhere also. It's not that complicated, so you can also program it by yourself in Python. It's not a big deal if you see the procedures which have to be done. But the idea is quite simple, and the idea is as follows. We again start with our measurement equation, saying that our output is generated by means of m times theta plus e, which is the one-step prediction which we derived yesterday. So we have m times theta plus e gives y, because in m we have the y's, the u's included, but time shifted, and that posed the problem. And E is this specific error, which is one part is the U values and subtracted from it the output values, but also shifted, which posed the problem. Now we want to introduce matrix W, please do not look at the properties 1 and 2. And we use this matrix to transfer the very first equation in a specific way. What we do is we want to multiply the matrix, the equation, this one here, with W. And sorry, it must be from the left-hand side. It's always a problem. Professors can't change. Distinguish left and right sometimes. So here we have the problem. So from the left-hand side, but to the right-hand side, I think this is just a writing mistake. So what I did is take W, whatever it is, as some sort of degree of freedom. I introduced just this variable W. I multiply from the left-hand side the very first equation. So we get W times Y, W times M times theta, and plus W times E. So that's the setting. And then I introduce new variables. I call them Y instrumental variable, IV, MIV, and EIV. It's just a replacement, right? So what you see here, it's defined that way. And this here is defined that way. And here, it's defined that way. Okay? So, and if you look carefully at the second equation here on this slide, you see, well, it's again a least squares problem, perhaps, but instead of looking at the original variables, I look at different variables, at different measurements and different errors, and also different parameter, different m's. So different measurements of u and the delayed parts of y and u. And if we do so, we can apply, well, some kind of least squares method again, as we did before. So we use the pseudo-inverse or the recursive formula, whatever you like. So everything we discussed the last 2 lectures. And then we end up with the solution for theta m as being the model parameters as to be defined as w transpose m to the power of -1 w transpose y. So that's the very result. It's easy at that point because just simple least squares. We reused everything because now, and the question is, well, what does it change if I introduce these variables or this matrix W? So first of all, let's try to interpret this result a little bit. So what happens if you have a vector and multiply the vector with a matrix? What is it geometrically? So higher mathematics, first semester, I think, algebra, first step. So you have a matrix and you look at a vector which is given in a certain coordinate system, and then you multiply this vector with a matrix. What do you make? What do you do? What do you calculate? Please feel free. There's some sort of rotation. So we very often speak of a coordinate shift. So make a change, a coordinate change. Might be a rotation, might be also something different, but it's a coordinate change. So it's just slightly looking at the same problem from a different perspective. And looking, and this makes sense. So it's like the first geometrical consideration of least squares problems is looking at the error from above or from the side and hoping to get rid of these the problem of being correlated between the shifted outputs and the measurements. So this brings perhaps some sort of different perspective and some sort of degree of freedom, because I have not said something about W so far. I just thought, well, take a W, look on take a different perspective of the same problem. Perhaps it helps. That's the idea. And let's see whether it helps. And the interesting fact, it helps. That's why we are doing that. Well, okay, but it helps. And I want to show you under which condition. The interesting fact is if this matrix W transposed fulfills certain properties, if in particular W transpose times E is in the probability limit equal to 0, and W times M is positive definite, then we can prove consistency. Sounds strange, but it works. And I want to show you that by a formal proof on the next slide. So if we have this kind of definition, if we find a matrix W with these properties, with W transpose E equal to 0 and W transpose M is equal to 0 in the probability limit, then we get a consistent estimate. Crazy. Just a change of perspective. Well, as I already said, carefully look at the assumptions, like in the research papers. So we have to discuss whether we can fulfill these properties, these assumptions, the first one. But first, I want to show you that if this holds, then we are happy. And this is given on the next slide. Even if it's supplementary material, it's nothing for you to learn by heart, but it shows how it goes. So let's take the same result. So this is our estimation we did with the least squares estimate. So neuropointers pseudo universe, we get theta m. Now we insert our knowledge about how the errors and how y is generated by the real system, and I insert it here. So it's just taking this equation and put it into this equation, and then I end up with this horrible matrix equation at that point. Okay, so I get W transpose m to the power of -1, W transpose m times theta, and then W trans m to the power of -1, W transpose E. Wonderful. So you might say, now let's have a look at the probability limit of the theta m. So what happens if we enlarge the number of measurements? What does it mean? M gets bigger and bigger and bigger because we have more measurements, but we have a set of shifted measurements from the beginning, then we shift to the right, next shift to the right, etc., etc. So we get a set of shifted measurements in y variables, so our output variables, but also in the input variables u, so the values which are inputted to the system. So if this is given, we can calculate the probability limit at theta mn, and look what happens. And now the wonderful thing, which is by definition given, if this is the identity matrix, obviously, which is given is identity, and here, if these two equations can be separated, which is the case, which are if the two equations are uncorrelated, which is by definition given, and if we further assume that W transpose E is equal to 0, then we end up with theta. So that's the basic idea. So far, so good. The mathematical technicality is still, well, can we do all the inverse matrix calculations? Yes, we can, because we said that W transpose M is positive definite. Every positive definite matrix can be inverted, so everything is fine. So that's our definition. Now the crucial question for this is where the mathematician stops and says, yes, I got it. For the engineers, the work begins, because now we have to look for W transposed in such a which fulfills these assumptions, the two, at the very beginning of the theorem 5.2, and this was this result was very early research for already in the at the very beginning of the last century, but finding wonderful candidates for W was not that easy. So the interesting fact, it appeared in the 70s, so 50 years later, which is quite a while, for this kind of problem. Wong and Pollack and Young realized that there is a good... Are there some problems? Yes. This year, because we assume that this gets to 0. The last one, this is, well, it's 0 by assumption, typical mathematical trick. We define the problem to disappear, and it's disappeared. No. The first part is in addition, it's positive definite, so it's existing. Yeah. So the latter part becomes 0. Yeah. It's wonderful. It's perfect. So perhaps I should indicate it here. Oops, sorry. Yeah. This one, this here goes to 0. Okay. And yeah, back to my consideration in the 1970s, Young and a little bit beforehand, Wang and Pollack proposed a slightly different solution. We got the following result. First, W should be composed of the U values, but shifted, and something else. So first the U values. I just want to motivate why U values are good. First recapitulate what we need. We want a positive matrix W transposed M. So it should be as much correlated as it can with M and W, which correlates very much. Remember what is stored in M. In M we find Y values and U values and shifted U values. So it's a good idea to put all shifted U values in W, then we can expect that it becomes positive definite, right? Or it becomes correlated, and if it's correlated, it becomes positive definite. That's the basic idea. So putting the U values in W was the first trick somebody proposed some years before, these three guys. And but one realized it's a good idea, but they stored the entire W matrix with U values, because then you fulfill two quite good. But on the other hand, what's about the first equation? And now you want to have second, it should be as much uncorrelated with the error. And the idea of Pollack can be proved is as a good candidate, is that we should use the predicted values of our model as output values. So if you look at H being the model prediction, which is given here, so be careful, H is just the model prediction. This is H. The model prediction should be as much as uncorrelated with E. Why? Because the disturbance is not present. That's the idea. Easy, but not provable. And the interesting fact is, again, engineering result, it works quite well. So that's the only thing I can say. So if you look in MATLAB, and this is the side remark, you find the instrumental variable method in the identification toolbox. You can put everything inside, and then you can use IV, you find IV methods, and they exactly use this thing. Can you expect that it works? No. Always. Could you hope that it works? Yes. And that's the engineering answer. Right? So it works quite well. If you choose W in that way, so this is just one specific row, you can put different shifted versions of it, one of another, and then you end up with a entire matrix W. It works quite well. So at the very end, yes, we are a little bit frustrated because there is no mathematical proof. As engineers, we are happy because it works. So that's perhaps the answer. Well, how does it work in practice? It works as follows. You start, so of course, same question as yesterday, what do we do with the initial values? Because at the very beginning, I don't have any model. I don't have any parameter. So we need some sort of a bootstrap. We should tear ourselves out of the mud. So that's perhaps the problem. And the basic idea is as well follows. Well, we start the estimation with the simple least squares problems. We know that it's wrong. It's inconsistent, and we use these parameters as starting point for our initial estimation for the model prediction. Then we fill in everything we fill everything into the matrix W, because now we can do the prediction, age, etc., and we can calculate the U values. We put everything in the W matrix, and then we apply our IV method. So we replace the Y values with the Y IV, etc., and then we end up with the second estimation, which is then done by theta M2 by W transpose M to the power minus 1 W transpose Y. So then we hope to get a better estimate, because we did this kind of transformation of coordinates and think that the coordinate change helps. With this estimate, we go on further and repeat the procedure, because it's better than we can expect to get better uncorrelation properties and correlation properties. And with that, we continue and continue and continue until there is no change of parameters. Therefore, the stopping criterion is as follows: theta mi, so one step before theta mi is compared to the one step before estimation, and if it's smaller than a specific parameter, which is up to our personal idea. I don't have idea. That's dependent. That depends on you. This is it's your decision parameter. So basically, if you look and do the things, it works really quite well. So typically it works good in that sense. If you do it in MATLAB, you have these estimation properties. Yes, we get a consistent estimation, and we are happy. And therefore, very often it's not checked whether we get good estimates in that sense. But be careful. Now you're trained. You know there are some prerequisites or assumptions about it. We cannot prove that this estimation fulfills the consistency check. We can just say we can hope for the best. That's perhaps like on Friday in the football soccer match. We can hope for the best. And here, the probability that it works is quite higher than on Friday. No, I won't say that. So it works quite well, but please be not frustrated if it does not work. So back as good engineering practice is to check, to double check with your experience, to double check with your knowledge about the system, to double check with whether it diverges. It's also possible. You get a divergent result. So there's no problem with the algorithm. No, there is a problem with the setting at the very beginning. Very often it helps to get a little bit better estimate, but if you don't know anything, that's a problem. Here is the corresponding theorem is again positively formulated. First of all, the conditions for a consistent parameter estimation by IV method, it works if these properties I mentioned are fulfilled. So this is the positive result. The only thing which we have to assume that the U values are mean free, so we use usually here an average value. So U00 and Y00 are the steady state values. You take the mean of U and subtract the mean, and then you get better results, because without it, you have a nonlinear system and you will have problems with that. So therefore, it's always subtract the mean. Yes. 2 slides back here. Okay. You shift it step by step. So you start with hk minus 1 and k is moving forward. So, and then you staple all vectors one up on another. Yes, yes. So for different case, and then you get like the mechanical writing machine, you shift always one letter to the right. That's the basic idea. Okay, so wonderful result, and also very helpful, and works perfectly. Perhaps I try to give you some light. So first this. Oof. Here we are. But no, not so good. What we have here, over there. Is it okay for you? Yeah. Okay. Well, weather is strange right now, I think. Yesterday, I thought I can leave my umbrella in the office and looked at the weather app, looked at the rain prediction for after the lecture, and thought everything is, I could go home or basically in the office without rain. But as you know, it was raining cats and dogs, and I was happy that was my institute and the secretariat and above had some one umbrella for me. So otherwise it would be quite strange. Okay, strange weather, and now it starts again raining. But today it starts during the lecture. It's even better than after the lecture, I think. Okay, well, this is the story about the identification procedures for linear systems. You might say, because everybody is talking about neural networks because it's already displayed. Well, let me tell you something. I discussed this with a colleague last week. Well, the linear things even work quite well in many situations because in many situations you're working around a working point, and so linear settings are working quite well, like the PID control. So you don't have to use rocket science if simple science works. So also an advice for you in practical applications, in particular if you end your university career, have your master's, a diploma in your hands, and you go to a company, it's always a good idea to start with the simple things first, and not with the, yes, I have an idea, I want to do the nonlinear optimization thing here, and then you have the traditional old engineer, 50 years, 60 years old, saying, hey, PID works well. Let's show that your method is even better. And my answer is very often you will fail with your results. So just as an advice, that's why we are teaching that. It's really old stuff, but it works well. So, and you're engineers, and please try to before shooting with neural networks on simple problems, use simple solutions first. First part. But this does not mean that complex problems do not exist. Which means we might have nonlinearities, we might have other things which are of interest, and therefore we jump into this topic right now. But back to our first consideration, it's a database method, this instrumental variable method. It's possible to identify the state space, the transfer function, but it's in discrete time. That's perhaps something we should bear in mind. It's discrete time, so we need sample data from a measurement, whatever. And that's the starting point. So measurements are needed, then we can generate a system. And if you want to do a first step towards, well, does it work? Do I get a control strategy? Yes or no? And can we apply, for example, a linear control first insight into the problem? It's a good idea to do it that way. I want to give you an example from a research project we did a couple of years ago, where I talked about this in various lectures already. It's thermal control of satellites, where you have to, you have the satellites in the orbit, and the satellites want to communicate via laser beams because it's quite fast. So it's really nice. So you have one satellite, another satellite, and one satellite shoots to another satellite. It's not James Bond. It's just communication, not to. But so you send the signals like SOS or so and to the second satellite and via laser beam. And of course, it's not like a pointer here. It's even more powerful laser, which is installed on the satellite. Now you have some sort of control problems. The control problem finding the satellite and shooting on that, it's not a trivial task because it's not from here to there, but it's from here to another site on the Earth, more or less. So you have 4 satellites around the Earth, and then you shoot always with a laser beam. That's the idea. That's something existing already, so communication structure, but also down to Earth, to a base station here on the ground. And a second task is if you have really powerful lasers, you need power. And these lasers consume power, they heat up. And of course, you need some sort of cooling. Well, the traditional working like a ventilator does not work in the orbit. Also, it's not a good idea to use some sort of fridge strategies, also clear. So usually what is used there is a heat pipe concept. I do not know whether you have heard that already, because it's sometimes used in computers to transfer energy from the main processor unit to another area where you can install the huge ways of dissipating the energy into the atmosphere. And the same works there. So you have such a heat pipe system, and which transports the energy from the heat source, so the laser, to some sort of heat sink where you use just thermal radiation into the orbit. It's important, of course, if you're sitting on the sun side, it's quite hot. If you're sitting on the moon side, temperatures are quite low, so temperature control is really a problem for electronic devices on such a satellite. And it's done that way. And heat pipes are difficult because you have 2 types of heat flows and the mixture of it. So you have some sort of a specific liquid which evaporates through a certain mechanism, and then you have a mixture of vapor and fluid, and then you have to describe this. It's a really complex thermodynamical process, and controlling these satellites is controlling the evaporation process is the task. And there's a control unit, and we were asked by one satellite company to do the control engineering. This is really a wonderful job because if you do mistakes and see the star on the sky because you did a mistake, then you know what you did. Because it was clearly that the algorithms will go online. So what we did is now in the satellites, and our first attempt was, well, they used PID control, and this PID control did not work well because it oscillated, and oscillations are not good for the laser beam, etc. So that was the task. And we started with a black box model this way because it was fast. We had measurements from the measurement chamber and all these, and we really started with this. It worked already well to design PID control. Not sufficient for the requirements they had, but for the initial beginning to design a good PID in this particular setting, it was later on we realized it's just PD, it's not PID without I, because I is already in the system. And that was the reason for, or one reason for the oscillation that was already interesting, because we realized already with such a simple black box model that there is no I. There is an I in the system. We had an integral part of this transport mechanism. So just as a first insight into that, so the PhD student did that, took the data and realized, yes, wonderful, it works well. So just to simply, instead of adjusting all the parameters, the 3 parameters of PID in the chamber, experimental chamber, we took the experimental experiments and designed it by the methods of the system dynamics and control lecture. So you can do the very same. And there I show you the white box model approach. Okay, but later on we realized that, well, if you want to gain performance, would want to have better results, it's necessary to get better models. And then we started to use artificial neural networks to describe the system. And also at the very end, we started with the white box approach and finally ended up with the white box approach because it worked well or better than the black box approaches, which does not say that black box approaches always work not so good like the white box approaches. So neural networks, and the starting point is just a mathematical consideration because, well, if you look at linear system, it's quite simple because you can describe a linear system always by means of a transfer function. You know everything. You know the structure. A transfer function describes any dynamical linear system with inputs and outputs. So you have the structure in your hand. Well, if we talk about nonlinear systems, just in the continuous time setting, it's like x dot is equal to f of x and u. Well, it's quite difficult, and because what is f? So compared to the linear setting, there we know it's just a linear mapping, and we have to calculate the mapping parameters. But for the nonlinear setting, we even do not know the nonlinear function. So, and if we are philosophically driven and saying, yes, we want a purely black box, we do not know anything, just data. Well, we do not know f. So the problem starts with what f should we take? What kind of function should we use? And that's a question for you. Before we start with any kind of sophisticated stuff like neural networks, what would you use from your engineering experience from the bachelor degree already? So it should be, I give you some hints. It should be a function which is useful in that sense that it can approximate always all, or almost all. What kind of function is capable to approximate almost all functions? Yes. Taylor series, exactly. So if you remember, if the function itself is differentiable, that's our assumption. If we have a differential problem, then Taylor series work. So polynomials in X would be a good choice. Therefore, it's not so surprising that at the very beginning, polynomials were used for these kind of universal function approximators. Universal function approximators. They have the properties to approximate almost everything. But one realized that a Taylor polynomial is perhaps not that good. Why? Who did already a Taylor series expansion? Raise your hand, please. Hopefully everybody, yes. Somewhere during the first semesters, you did the Taylor series expansion. Have you ever plotted your Taylor series expansion from a sine or cosine or so? Yes, already? No? Something else? Exponential function in a Taylor series? So which one worked better? Yes? The exponential, so the approximation of polynomials with exponential or exponentials with the polynomials works even better than sines and cosines. So it was, you realize that these kind of functions are not so well capable to approximate almost everything, even more complex nonlinear functions. In particular, if you have periodic functions or so, then you will face problems. So do this, take MATLAB, do the Taylor series expansion up to second or third order, not what we do usually in system dynamics, just to the first order, linear parts, no, nonlinear parts, and plot the function and compare it with your Taylor series expansion. You will see there are some differences between the two. Of course, we have nice other properties, like we can calculate the remainder, we can calculate the error, but we only know that close by our development point, everything is fine. So that's the knowledge we have. So Taylor series are not so bad, are also used. So I don't want to say anything against Taylor series, but later on one realized that a different strategy worked even better, because McCulloch and Pitts realized that if we look in our brain and look what the brain is doing chemically and electrically, you realize that's the wonderful function approximator. So I put it in that setting because it was exactly that. Of course, driven by the fact we want to replace the human brain, and you see, it was 1958. It's not today. It's not AI revolution. It's 1958, and if you look for that, they realized that the human, if you try to mathematically describe what the neurons in the brain are doing, you end up with some functional mathematical description we want to look at in a second, and a certain property which obeys such a universal function approximation capability. And that's the wonderful fact why it's so powerful, besides other things. But from a mathematical perspective, it's exactly like this. We use the model of the brain more or less as a perfect way of describing F. And then we do the very same we did before, and therefore I did also the linear part, because the nonlinear part is not even more difficult than the linear one, because it's, again, a fitting problem later on. So let's have a look at this kind of neurons, because if you look in the brain, you find two things. First, the neuron and the interconnection. So there are two parts. Interconnection. So we have some sort of network structure. And this network structure itself is also a second part of the story. So you have simple functions which are interconnected in a, well, fully interconnected, partly interconnected, whatever way. But by nesting the function one into another, we get this universal function approximation capability. And this should be depicted here. So you have some sort of this function approximation neurons. So the circle describes the neuron. With a simple function calculation. We want to look at that. And their interconnection. So what happens if you interconnect one function into another? Well, you insert one function into another. So if you trace, for example, this part, you start here, function 1, this part, here's function 2, 3, 4, 5. I just want to traverse this part here, and 6. So if I enter here, what happens? So down below, I insert F6 into F6, F5, F4, F3, F2, F1, and U, and other things from the other connections. So it's more or less always inserting functions into functions into functions into functions. It's something which always applies to polynomials, but here even more complex. mathematically, it's a horror. So because function into function into function, but there are some properties which we can use. But that's the basic idea. And with that, if you use specific functions, f1, f4, f5, f6, then you get a good result. Now, the wonderful part of the story is the functions are almost the same. We always use the same, almost the same function inside. That's the idea. Then we make exactly what we did before. We have our input, we feed it into our neural network, and look what's coming out of our network and compare the result with the measured data and say, okay, perhaps there are some pre-parameters which I can adjust such that it fits. So it's again a fitting problem. It's like before. So there's something we did already in ODS. It's nothing else. It's just a fitting problem from this simple perspective. A special one, but it's a fitting problem. And we solve it in the same way. We have to calculate some sort of error measure, a measure of the error between the predicted output and our real output. Adjust the parameters such that the predicted output and our real output fit. That's it. The only thing is, neural network guys, and I love them very much because we work quite a lot together, speak about training, which sounds even better than just optimization or something mathematical things. They speak about backpropagation, which we might have heard already, instead of gradient descent and line search, which is not that cool. They speak about a neural network instead of saying it's a nested function. So be careful of that. I'm kidding a little bit, but here, very often we realize if we work together that we speak about the same thing, but we use different names for it, for the same things. And very often my AI guys are very, very creative to produce crazy names for meaning something mathematical simple. That's the point. But at that point, it works wonderfully well. That's the interesting fact. But back to the origins. It was already 1960 to where this story started, and then we had 3 revolutions of AI already. So we have the 3rd one right now. So at the very end, we have some sort of this kind of model error which we looked at, and now we have to look at how the error is composed. Usually, if you do this kind of fitting problem, you have a set of data which you use to fit to the data. And of course, as you know from the lectures by Eric Sachs and others, that it's not always good just to train, it's also, or to learn, or to fit the data. It's always necessary to validate whether it's working. And of course, it's a good idea not to use the same amount of data for validation phase and, or verification of your approximation capability. Therefore, if you have this box of data, you split it in 2 halves and take the first one for training or approximation fitting. Sorry, I use it synonymously throughout the lecture here. So for training, and the second part for validation. So we have some sort of training phase and validation phase. And what typically happens is the following. I should start with the following observation, because McCulloch and Pitts and Rosenblatt started with a simple neuron and asked the question, well, can I use it for just one function? What can one function do? with one function simply. And this is something I learned still during my PhD, not 1970s, but later. From a theoretical perspective, what is possible with that, and you can do nice proofs around that, etc. And this was, well, quite a while ago, but a lot of research in that area. But one realized one neuron is not good enough, and this interconnection is necessary. So this network capability, if you like. And now the question is, back to this slide, how many neurons you should put inside? There's a crazy answer, but how many neurons are necessary and how many neurons are good? How many functional approximators? But and we can speak of the totality of neurons. First of all, I count them all and look what happens. And first of all, we realize the following: if you have more parameters than measured data, you can expect that the measured data is fitted perfectly, right? But then the following happens. If you say, okay, I have a huge number of neurons, a huge number of possibilities how to adapt, then I will fit the training data perfectly, but I cannot expect that the validation data is also perfectly matched. That's the problem. That's something one observes, and it's called a variance error during the validation phase. Whereas the bias error, so the difference between the training data and the true parameter training data and my model data, is small. On the other hand, if I use less neurons, less freedom, I cannot expect that I get the fundamentals captured. And therefore, there's some sort of trade-off between the number of neurons and the number of, depending on the training setting and the complexity of the problem. This is sometimes called the bias variance dilemma, which appears. So it's a question. You replace the question of what is F by means of how many neurons first, and you replace the question of what is F by how many neurons and how many intermediate neurons. Take it like this. You can also talk about layers and say one layer, another layer, another layer. Just to clarify just one word, if you have very much layers, a lot of layers, then we speak about deep networks. If we have just one, it's not deep. It's just some intermediate layer. And here comes the funny fact, just as a side remark. It's a very, very old result. Nobody knows, but because everybody talks about deep neural networks, which work very good. But at that time, mathematicians proved that just one layer is necessary to approximate almost every function. Interesting, isn't it? So just one intermediate layer, so one output layer, one intermediate layer, and a second layer, a third layer for output, is necessary to approximate almost every function, and there's a formal proof for the approximation capability. That's why in that time it was the result was found in 1990s somewhere. I think I have the date somewhere in the slide, so I do not remember it correctly right now. There, everybody's seek for just one layer neural networks and try to train that because everybody realized, yes, more is not necessary. This was also due to the computational power because training deep neural networks is more complex than just one layer. So everybody talked about the number of neurons in the hidden layer, so-called one hidden layer. Hidden, by the way, because it cannot be seen from the input and the output. That's That's the way it goes. Well, this is initial remarks. Now the question is, how do we do it? Okay, very often the problem splits in these two phases: a training phase and a validation phase. That's depicted here, and then we are confronted with this optimization. I'm sorry, here with this optimization problem to get the error between the true data and the model prediction data small, and that's something we have to talk about how we do that. But first of all, I have to talk about the very ingredients of this neural network. So what is this specific F1, F2, F3? I ask you, have you heard something about these different Fs already? I think some of you might have heard lectures in neural networks already, so perhaps you can name some. Yes, yeah, here. Sigmoid function, something else? Yeah. Relu, something else? Yeah. Hyperbolicus, yeah. Tang-Ha. And sometimes you find also Gaussian heads as functions. These are called generalized neural networks. So we talk about them all, just listed them. But the basic principle is always the same. Just to explain the neuron, here is it. Here's the circle, big circle. Now just we zoomed in. And what you see here is how the calculation is done. First of all, I capture, I take the ensemble of all input values. I named them I here to get rid of the, or get a little bit familiar to the neural network communities. So there is I, and these values, these are mathematical values, so real values. One single real values is now multiplied with a weighting factor. So just a second number, W. And for each input, I have a weighting factor. That's the basic idea. So WKI is multiplied with II. And in addition to that, I can add some positive, negative value to it to adjust the level. It's a sort of threshold. And then I put everything, insert everything into a function f, and we have to look at this function. That's the function name, sigmoid function, all that. So if you look at this, you can see this as a vector I, which is then multiplied as an inner product with the W values, and that's it. Important, up to now, the W values are not known. So W is free, and we have to adjust the Ws. I's are the values which are entering as inputs to the problem. So back to our overall situation. So if you look at the circle, this value enters here, is multiplied with a W. And if I draw these different lines to other neurons, it just means it's the same result because you have just one output. This is a specific notation of a neural network. I can also draw it like the electrical engineers are doing it and connect it with a dot. So it's always the same result. There are no different results here. So what the neuron outputs is then transferred to this neuron, to that, to that, to that, to that, to that, if it's fully connected. With this, we have the output, and as you see, OK is the output, and here important, it's always the same. It's nothing different. The parameters W have to be adjusted, and that's something we have to talk about, how we do that. But these are the three parameters. These are comparable to what we've seen in the linear setting, A and B. It's the same thing. And we are seeking for A and B, or here in our case, W. That's the setting. But now you can imagine, well, the optimization problem which you're facing, it's more difficult because now at every line, which is drawn here, you have one W parameter. So now you can count. It's obvious because, well, I think almost everybody heard something about the ODS lecture, and there I talked about the problems with millions of optimization parameters. Here is one. The more neurons I put inside, the higher is the number of optimization variables, the higher is the workload for the computer to find the minimum, right? That's it. That's the second answer why the neural network story started now, or over the last 10 years, perhaps, if you like, and not during my student's life. Because when I was a student, I was also fascinated by these neural network things, and heard a lot of lectures about it, did in the informatics department, and then realized, well, in control engineering, it does not apply due to computational reasons and approximation capabilities and all that. But here is the answer. At that time, we had not enough computer power so far for optimization problems to do the story. And if you look in the 70s, even more clearly. So, well, that's the basic idea. Now let's have a look at the different functions. Here you find the hyperbolic tangents. What you talked about looks like that. Might be also this, never used. So in my practical experience, I should erase it. Sorry, wrong here. Well, should erase this from the slides. Third, something you mentioned, mostly used, the so-called sigmoid function. Sorry, I put it here. There's the mathematical expression. It's 1 over 1 plus e to the power of minus x minus c. And this is interesting. Why? Because this is somehow similar to what we find in our brain. Because there you realize that if a certain threshold is arrived, then the neuron gives an output. And the neural network guys speak of firing. Sounds even better than just you have an output. But this is neuron. This is also the medical guys are talking about. So it's the neuron is firing, gives a signal out, gives electrical signals, and it's a complex chemical process which is working there, and it can be easily approximated that way. It's the easiest model of that. It does not say that's what we have in our brain exactly, but it somehow replaces that. And so if you're higher than C, so in this case perhaps 0.5 value, then you can expect that the neuron gives maximum output, and then it's the maximum value is reached. Very often, for computational reasons, the so-called ReLU function is used, which is depicted over here. It's somehow an approximation of what we see here. It has some nice properties because in this intermediate part, you have a linear function, and then you get simple linear optimization problems, by the way, and at the bounds also. So sometimes step functions are used. This was the early age. McCulloch and Pitts worked a lot about not working with the sigmoid function, but with the simple step function. But then you are in the area of mathematics with discontinuities. It becomes really complex, and they try to research for what happens with 1, 2, or 3 neurons. What can be approximated with that, with this kind of step function. And what I already mentioned, sometimes the so-called Gauss function is also used. Well, these are the functions. Basically, it's this one and that one. So if you look in today's practice, you find this and that. Okay. Now, what is needed? I just want to talk about a specific structure which is very, very often used. It's a so-called multi-layer perceptron. It's something we constructed right now because we have one neuron. It's called perceptron. And multi-layer means we have a couple of layers of it which are fully interconnected. That's the setting. And the task is that we have to adjust the weights of each neuron, and that's necessary. I just want to depict what is possible. Of course, sorry, back to that. If you have P inputs and N outputs, it's impossible to depict what I have in my hand. I just want to show that it's possible to describe nonlinear functions with that. Okay, that's the only way. And therefore, I boiled it down to a simple structure, just 2 inputs and 1 output, because then I can describe the nonlinearities by graphically depicting the mesh plot. And you find it here. Here, for example, 2 inputs, sigmoid function, 1 sigmoid function, and there you find the nonlinearity. So it's somehow looking shaped like this. So if you have functions which look like this, it works well. Similar radial basis function network, which is a little bit more complicated, it looks like this. So what is different is a little bit more concentrated, right? So it operates in a certain regions there where the Gaussian heads are placed. Therefore, it works for these kind of problems. And last but not least, sometimes also division in between. That's the so-called generalized regression neural network, and that's it. So I have no picture of it. Well, up to now we have just a let's look at this simple first one here. I have a static relation, right? So if we look at this neural networks and the multi-layer perceptron, I mean, we just have inputs and outputs, and the input-output relation is static. Everything I input gets calculated, and immediately you have the output result, except the calculation time, which is needed inside. Of course, this produces also a substantial problem if you have not just 2 or 3 inputs and outputs, but trillions, billions of neurons or perceptrons. That's why we have the discussion right now, what's about the energy consumption of neural network calculation. So neural network training is one part, and the second is the consumption of electrical power if we want to do the calculations, because you always have to evaluate sigmoid functions, not just once, but millions of times. And if you remember your classes on how do I do the calculations of an exponential function, because it's part of the sigmoid function and the division in a microcontroller or whatever you like, or in video computing thing machine. It's something which has to be split into simple mathematical operations, and so you see it's quite a lot which has to be calculated if you calculate an entire neural network. So it's also a question of that. So at the very end, we end up with that. But what my main message is, the very first ingredient or the very first message is that it's a static input-output relation. So comparable to what we did in static mapping, find a simple regression problem, but now a nonlinear regression problem. That's it. The question appears, what can we do about dynamic systems? And I give you the answer here on this slide. Well, there you see a state space model. It's similar, but instead of feeding just the inputs into the neural network, which is here given, you feed a little bit more in, also the delayed outputs. You can do this with the outputs, you can do it with the states. So it's the simple trick we used before. So you use your result delayed one time step and you get the output. So you have the very same thing for dynamic systems, but instead of using just always only the inputs, you have to reuse the outputs but delayed for one step. So you net, oops. No, it's not possible, Felix. That's the basic setting. And with that, we have everything in our hand. And the question is, what can we do to train the network or to learn the parameters? Because we have millions and trillions of parameters which have to be adjusted. And I just want to give you a simple idea, because the training procedures are more or less always the same. Something you should do by your hand always. I have a colleague in the informatics department who says that every informatics student should be capable to should have programmed such a training procedure by hand to see what happened. Not do like Google or so, just for a simple result, not to be as performant and do all the tricks. That's not. Here is somebody really. It's not that he writes. I tried to translate. It's not that important. I tried to. Yeah, nice. Okay. Next time he will be in the lecture hall. Okay, that's why. Now, it's how we do that. I have to tell you, at that point, it's a huge topic. So please feel free to start here with additional lectures. I stop here. I show you this very simple training procedure. But our intention is not to show you all the results of deep neural network calculations and all that. It's the basic idea is always the same, and there are some tricks how to design these networks. You learn something about what kind of layers are in between, what kind of feedback structures. I showed you a simple one. There are different structures also. So please feel free to look in these lectures, basically in the informatics department, but also starting here in the electrical engineering department by, I think Laurent Schwan is giving some lectures in that area, and etc. Because he's using neural networks for transmission of information via some channels and so on. Therefore, you find also something there, but basically it's in the informatics department. For us, our intention is to train the dynamic behavior of the system itself, and you should learn the basic properties here. Of course, everything is well encapsulated today in tools, and tooling is a important knowledge. Nothing which is trained here, but has to be done in practice by you in that sense. And okay, so training, that's the last part of today's story. Well, at the very beginning, first you should remember ODS, the lecture on optimization, that we simply have an optimization problem here. It's the difference between the predicted output of the neural network and the true output of the measurements. And we build a performance index of it and try to minimize it. That's it. And then you can say, I can stop here. I can apply everything I have in my hands, like source region methods, interior point methods, sequential quadratic programming, whatever you like, line search methods, Newton methods, And the interesting fact is that one famous line search method is used here, which is called gradient descent. And gradient descent, well, the informatics guys talk about backpropagation. And the name is very, very helpful because at that point, the name shows how the method works. Why? And that's what I want to show with a simple example. I assume that we have just one hidden layer to reduce complexity in the notation because you get frustrated with neural networks. You have here an index, there an index, there an index. It's always a little bit strange. It becomes overly complex in terms of indices. So the basic idea can be captured already with a simple hidden layer. But one hidden layer is needed. Otherwise, you won't get the idea. So what we think is we have one hidden layer with m neurons. So it's given here. We have an input layer, which is just a linear mapping, and an output layer, which is given here. And we set the threshold at the very beginning just to 1, which is just an assumption, but can be discarded later. So if we do the calculation of one output of the neural network of the multi-layer perceptron, we have what? The activation function, our sigmoid function, remember? And then it's inserted the parameters of the activation, the parameters of the output layer, which I call WO, multiplied with all activation functions in the layer before, and inserted in this layer, we find a WI, the inputs, times the inputs, because it's a linear mapping. That's all. Well, so what you see is a nested function, a function of a function, and in between you have the parameters WO and WI. Well, now I set up the minimization problem, which is given here, and the minimization problem is just J as being the difference between the true values, T, and our predicted values, O. It's not very intuitive, T and O. I don't know why I used that. So, well, that's the measurement and the predicted output. And with that in our hands, we want to minimize this performance index. And then you see, okay, wonderful. It's just quadratic. We learned something about this. Let's take gradient descent, and we're happy. So we apply gradient descent. Well, then you know something from your higher mathematics class, and it's important. And also at school, you learn something about this. You know the chain rule of gradient calculation, right? So derivatives. And that's why it works so nice, because if you have a sequence or a nested function, you can apply the chain rule. So the gradient is calculated by means of the gradient of the outer function multiplied with the gradient of the inner function. That's the idea. And that's depicted here. Sorry for the indices. I just wrote it out to show you. It looks horrible, but it's simple. And the only thing I did, I encapsulated all the gradients, all the parameters here. So writing down the performance index, and then I tried to derive J with respect to the performance index, which is given here, the first order derivative. Then I insert, I look for the first order derivative of this, which can be then split into two parts because we have this nested functions setting. And now we apply exactly the chain rule. So we can use the inner derivative and the outer derivative, which is given here. So first, the activation of the outer part with respect to this input, multiplied with the activation to the values W of the outer values. So we can replace it that way. And the same applies also for the inner part. So obviously, it's a repetitive structure, right? So it's always the same. And if I add something like and an additional layer, it happens again. And an additional layer, it happens again. The only thing we have to learn computationally is how to glue this all these things together. And the interesting factors like the fast Fourier transform, there's backpropagation shows you how to glue the things together. And the idea is lastly depicted here in the last slide. So a last equation, which is given here. So the derivative can be calculated just as a multiplication of various values, which are given here, and derivatives, and the deviation from the true output and the predicted output. So what do I need? I need the derivatives at these various points of each particular neuron, if you look at the functions there, and the deviation. And the interesting fact is we can observe, we can calculate the bad weight changes independently, and the output deviation between the predicted output and the true output also by just propagating it forward through the neural network. I get, if I just apply the inputs to the neural network, I get the deviation, and then I propagate back if I calculated the derivatives individually for each activation function and store it in each neural network, in each neuron, each perceptron. I just get the derivatives and then I glue this together. That's it. So it's quite simple: addition and multiplication. That's it. So therefore, we have this kind of forward structure, and here it's somehow shown for a simple forward structure without any addition and just a network and a neuron and then another neuron. So first of all, I propagate the value x, I get g. I can also calculate g of x, g prime, which is the derivative, in the same step. Then I calculate g of x. G of x is inserted into f. I get f of g of x. That's the forward step, but also the derivative can be calculated f prime g of x. If I now back propagate the same thing with the 1 here, I get 1 times f prime g of x, and backwards I have just to multiply due to the chain rule f prime of g of x times g prime of x. That's it, which is stored in the neuron. So first forwards propagate, and then backwards propagate, and that's it. With the backwards propagation, you get the derivative. With the forward propagation, you get the deviation between the true and the real, the true and the measured value. And with both steps, you can calculate the gradient of the neural network at the specific point and the output of the neural network at the specific point. And then, if you remember ODS, you have everything in your hands. Because if you remember line search with gradient descent, you just need the gradient at the specific point. So you need the point, of course. And then you need some sort of a step, right? And then you make the step towards the gradient or along the gradient. That's it. So backpropagation obviously needs something like the step size, right? That's something gradient descent methods need. Very often it's called training constant or learning parameter or something like this. It's not called, sometimes also step size. So you find both. It's step size. That's something you know how far I go along the gradient. And of course, all the tricks apply. We learned in ODS, like automatically adjusting the step size, have it manually in our hands, and always use the same, adjust it to the gradient situation. And of course, all problems apply, we know from ODS, right? So also in neural network, what we know from optimization, we know we can be trapped in a local minimum. Same happens here. It's possible that we get poor performance in terms of convergence rate. Same happens here. We can have good performance. I don't want to say it's always bad performance because professors tend to say it's always bad performance. No. So you have all these advantages and disadvantages of everything we learned in ODS. So please keep that in mind. And there's nothing new about it, but it's sometimes termed a little bit differently. That's it. So this is just a rule of thumb, but I think it depends really on your problem, how many neurons you use. Last but not least, you get here some things I mentioned. I really want to, and then we stop. Sorry for this 2 minutes. First of all, what's about the approximation capability? I mentioned something about that supplementary material because it's just really a small portion of it. There's a vast literature on it. First of all, there's a so-called universal function approximation theorem, 1989. So by the way, in the 90s. And sometimes it's not known anymore. That's the interesting fact. So I find it really interesting. So the following, the theorem says that only one hidden layer is necessary if you want to approximate one continuous function. This forced our research into to go in the basically wrong direction compared to Eddie. Motivated to use just one hidden layer, and until the last years when the deep neural networks appeared in 2010, 11, 12, so somebody realized, well, they are not performing so bad. So the question is why? Because there's a universal function approximation theorem. And in the 2016, first papers appeared in neural network information processing systems, for example, which show that there's some sort of expressibility of deep neural networks which are better than the flat structures. So, but until now, it's not completely understood why it's the case, but it works good. So that's the problem. But with the price of having to calculate these deep structures, and that's why all theoretically working guys in the 90s said, well, I'm happy because my computer power is limited. I stay with the one hidden layer. I have to calculate all these things. Before now it's possible. And that's why you see all the nice, so NVIDIA things and possibilities to train the networks. That's for today. See you next week. And then we go a little bit towards the question, is it possible to, right now we have pure black box, and I want to motivate, sometimes it's helpful not to do pure black box. Can we use additional physically informed things to get better approximation capabilities? Because usually we are not completely knowledge free. But we have knowledge about our situation and whether can we use this. So that's the question of next time. Have a good day. Bye-bye.